Okay, so we will finish today about the water and the ice. Then we are going to go over the slides after this. We talk about the sorption, desorption, all those things. There is one important thing we haven't mentioned. It is related to the microbiology, which is antimicrobials, but there's lots of chemicals there. Is chlorine water. So we want to mention about this in the food chemistry class. So during the pandemic, you all know that. Let's say I have a bottle, some bottle like this. I'm not very good at drawing. Okay, a bottle like this. We call Clorox. Okay, this is a $5, 1 gallon. Pretty cheap. And if you look at the label, they said 5% sodium hypochlorite. But the other ingredients, they say it's a water or the other things. And this is a chlorine water solution, or we call it a bleach. We have a common name. And this is widely used in the fresh produce industry to killing bacteria because it is easily to be prepared. So we say it's easy prepare. It is cheaper compared to lots of the other antimicrobials, and has a very strong antimicrobial activity. And the approved to use the concentration, it is no more than 200 ppm, parts per million, on food contact surfaces. And on the chicken products, let's say in the chilling tank, it is allowed to use up to 50 to 100 ppm. This is on chicken processing, like chilling water. Okay. And this is my other class. We want to talk about details, so we're going to skip talk about here. Not going to be that detail here. Talk about antimicrobials. However, there's a lot of the chemical behind it. So what is the major components of this chlorides? We're going to draw the equation here. Cl2. If Cl2 dissolves in the water, it will happen a very simple reaction. That is even in high school chemistry book. HCl and HClO. There is a two acid generated. This is hypochlorite gases. I want to make sure the spelling is correct. This is a hypochlorite acid. And the HClO, it is hypochlorous. CHL, hypochlorous acid. And the HClO, hypochlorous gases, referred as free chlorine, acronym using FC. Because we think in the chlorine solution, the most effective antimicrobial agents is actually free chlorine, which is hypochlorite gases. But I want to also tell you, this product here is highly related to the pH. Now what happens is, this HClO, it could also go another direction. will generate proton ions and ClO negative. This is, we call it a chlorine ions, which is a scientific name, hypochlorite ions. And in the chlorine industry, or we say those water industry, they call HClO together with ClO negative, which means hypochlorous acid and the hypochlorite ions. This refers total chlorine. And there is a chlorine meter you could test it. We usually in the lab we test the free available chlorine. But there is also another test that can test the total chlorine. Total chlorine, which means everything is together. Now there's other minor ingredients, but we're not going to mention here. So what is going to be the curve looks like? The curve kind of looks like interesting. It is like this, like a rectangle. Okay. The x-axis, it is actually a pH. This y-axis, we call it hypochloric acid concentration, and we using 100% to express it. And this here is chlorine ions, which is hypochlorite ions. And we go this way, so this is also percentage, but we will be label these as 0, 10, we go 20, 30, 40, 50, 60, 70, 80, 90, we go this direction. This is we go the lower direction. So we go here, we go 10, 20, 30, 40, 50, 60, 70, 80, 90, we go 100. So what going to be these curves be? Very interesting. It's rely on the pH. So we're going to draw the pH line here. It starts from 4, 5, 6, 7, 8, 9, 10, 11, and by the 12. What's the curve will be looks like? It's very interesting. The curve looks like this. This is well explains the impact of the pH for the concentration, for the level of hypochloric acids and for the chlorine ions. So HClO and ClO ions. So you see here, at 4 and 5, accurately should be like 5 or 6. The chlorine ions, the hypochloric acids, hypochlorous acids, which is free chlorine, is the highest level, at least 90%. And what happens for chlorine ions? Very low, less than 10%. The pH increased. When they go to alkaline solution, passing 9 to 10, HClO is dramatically decreased, maybe only like 5 or 10% left. But at the same time, the chlorine ions is dramatically increased to almost 100 at the end. This tells you something. When you buy a bucket of Clorox, and we call it a bleach, and then you open it, turn it on, and you dissolve in the water, and then you're gonna have to spread on the surfaces. It is actually does not have a much antimicrobial impacts, because if you measure a pH of this Chlorine, it is a pH around 11 to 13. So it's actually right here. It will be a dominance of chlorine ions, very limited amount of the hypochlorous acids, the free chlorine. So what we do, what's the industry they do? They are trying to let the pH in this range. The produce industry, they add citric acid. That's produced in the industry. The chicken industry, what they do? Bubbling carbon dioxide. Because we are pumping bubbling carbon dioxide, it will become a weak acid. Carbonic acids. That's what the chicken industry, the poultry industry did. Okay, so that's very important. Now, we also want to talk about something else. How about the opposite direction? And I want to tell you, this is also very, very interesting. Okay, when you have this guy, it could go this way, it could also go the other way. We're going to go the other way. If you're adding too much citric acids to lower down the pH, it will generate this guy and water. Go back. Actually, easily say, go back here. What is this then? This is chlorine off gas. That's not good. The chlorine off gas will let you curing. And I tell you one thing, what happened is, back in 2011, when I was a postdoc at USDA ARS at Beltsville, Maryland, I work in a group which is we do the fresh produce safety. So we went to California, and this is, let's say this is California, okay, briefly. You know that. This is San Francisco, LA, Los Angeles here, and San Diego right here. The Central Valley, there are three major produce industry, which is Dow, Fresh Express, and Taylor Farms. And we work in one of the subside of the Taylor Farms. A company, we do a pilot plant try to see the chlorine with some of the surfactants to see the antimicrobial on the fresh produce, on the spinach. And we work there the whole day. Because chlorine is very easy to working with soil dust or those organic matters. Those organic matters could be low down. The 50 parts per million to 0.5 ppm in 30 seconds if you have organic matter, which means soil dust, all those things. So what they do, they measure in the pH, they measure in the chlorine concentration, the free chlorine concentration. Once it's go down to less than 10 ppm, what they do? They re-add Chlorine. But at the same time, what happened? This pH level gonna lower. And then the off gas is coming out a lot. You work there about 3 or 5 hours in those plants, you have to have eye protectants, goggles. Otherwise, you're gonna be curing. like crying, not because you're sad, because those chlorine off gas is horrible. So that's why I want to tell you the pH control is very important. Now based on this one, we have another nice table, could be showing you, relatively easy to understand. Okay, y-axis, this is a chlorine species. And we say 100%, let's say. Okay, we could do, just make sure a little bit easy, 20, 40, 60, 80, and on the top 100. And the x-axis, it's still the pH. But this time we're going to do like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we do 12. What's going to be the curve looks like? It's very interesting. The curve kind of like, what's the first curve? HClO. That's free chlorine. And the peak value, you see up right here. Fresh produce industry thinks the peak value is pH 6.8. Poultry industry, they think it is around 5.5, little bit difference, just based on their experiences. I don't know why. I ask lots of people, they just say we use citric acid, low down pH 6.8. Now we have another curve. What's the other curve comes out? This curve is interesting, and we already mentioned, like this. It's almost 100 when you go 12. Chlorine ions. Then we have another curve. What's the other curve? The other curve I use yellow. What's that? Off gas. Chlorine. So, these two curves tell you the pH is the key. Now, a very small fresh produce industry under the poultry processor in West Virginia, when we have extension course, we told them what you can do is maybe combine with a little bit of vinegar water to lower down the pH. And ideally, you should use a pH strip to measure the concentration. But I don't think lots of people are going to do that. But at least you, based on our calculated chart, you should add a little bit of vinegar water. It also helps. Vinegar water. Because the vinegar water basically is 5% acetic acids. That helps a little bit to lower down the pH. Absolutely is not using the original Chlorine to do the cleaning. It's not going to have much impact to kill bacteria. Definitely need to lower down the pH. Second, there is an organic matter there. So, using the chlorine, always remember, you touching surfaces, your food contact surfaces has to be cleaned first. If there is so many soil, dusts, even food soil there, treated as organic matter, it will be low down the effective chlorine concentration to nearly minimal concentration very, very quick in like 30 seconds. So very simple, you prepare a chlorine solution. If your bucket is already dirty, you can just pour it, because hypochlorous acids will go down to 0.5 ppm very, very quick. Okay, so we talk about this chlorine water. It's very interesting. Chlorine water in the United States used to be the #1 for the poultry industry during the chilling tank. Right now it's not. It's a peroxyacetic acid, it's a PAA. We're not going to talk too much about that because it's a food microbiology class. It's a job to talk about that. In EU country, when you do fresh produce, treated fresh produce, post-harvest treatment, and the fresh under the chicken meats, you cannot use chlorine. Why? Because if you're using lots of the chlorine, they will generate THM. That's called trihalomethane. It's 5 chemical components. One of them is chloroform. Trihalomethane, they treat it as a carcinogenic chemical. Will cause cancer, possibly, especially like a bladder cancer, this kidney cancer. Some research talk about that. So in the EU country, they cannot use chlorine solution, the Chlorox. What they do, they created something relatively new, relatively smart, but I do not think so. So I will explain to you. This is called electrolyzed water. It is a very smart one. So what happened? I have this container, a tank, let's say. This tank, I'm going to, at the beginning, adding electrodes. Okay, this is a electrode. Electrode have two charges, which is positive charged and negatively charged. The positively charged, we call it an anode, and the negatively charged, we call it a cathode. This is everybody knows. And we put the water there. Okay, I'm going to put the water. So I put the water molecule there, H2O. Now what else I put? It is really smart. I'm adding salt. I just simply add salt. Sodium chloride. Now, of course, if you want to generate something, it needs to be used in the food processing plants. That has to be food grade. You cannot use a chemical grade in the chemistry lab to do it, food grade salt. Know what's going to happen? Turn on the electrode, they're going to have a reaction. What's a reaction? And remember, this with electron will have, this comes out, and this. Salt, dissolve in the water will generate sodium, positive charge, and chloride, negative charge. So what happened? This is negative charge, the negative charge is going to go there, and the positively charged, and the positively charged, the sodium and the proton ion is going to go there. Then what's going to form there? You put all these together, they will generate at anode side HClO. Is that very smart? It is a free chlorine. What's going to happen here? Sodium hydroxide. So they treat this guy is a sanitizer, which means it's antimicrobials. Going to be killing bacteria. And how about that guy? It's a cleaner. It's like a detergent. So they think the liquid coming from the cathode, we got to clean the surface first. And then the liquid coming from the anode, we're going to use that as antimicrobials. Works very well. What's the disadvantage to do at the beginning? This side, because the whole water is mixed, they generate lots of the proton ions. So what happened? This guy going to become very acid. So at the beginning, it's acidified electrolyzed water. EO water, they say EOW. This is very corrosive. Acid is always corrosive. If you ruin the metal surface, it's going to become decayed very, very quick. So they're using methods. Later on, they put up some membrane system here. This membrane system can do neutralizing. Because you have this comes out. This is a very strong alkaline solution, and this is an acid solution. If they mix a little bit well, will become a neutralized electrolyzed water. So this is what happened in the recent 20 or 30 years. It sounds very smart, but did they really solve the concern of trihalomethane? Doubtable. I haven't done that yet. Just want to share with you, we have a literature review later on. I had one paper published at the Food Chemistry Journal back up almost 9 years ago when we modify the produce industry. What they do, when the free chlorine below 1 ppm, we're going to re-add free chlorine. We add then again below 1 ppm, we add free chlorine. Then we testing trihalomethane. It's dramatically increased. And later on, the trihalomethane is accumulated a lot. Because the trihalomethane really depends on is HCl. And this is HCl also dramatically generalized from the electrolyzed water. So it is very suspicious. Even you use electrolyzed water, does not mean there is no trihalomethane generated. Might be the amount can control a little bit, but I will tell you there is a lot still going to generate. But I haven't done the research yet. I'm always interested to do something about that. Just want to share with you. But electrolyzed water in European countries, they are proved to be used a lot during the post-harvest processing. And a couple of years ago, there is a system named by Trust Water. And the principle is just like that. This Trust Water is $70,000. Equipment looks like a refrigerator. Home refrigerator is $70,000 to generate electrolyzed water. Okay? So this is something we talk about chlorine water and electrolyzed water. Electrolyzed water have a slides and the chlorine have a slides. We can talk about that. So next one we want to talk about is ice. Do you mind just move it? So here we finish about the water basically. We want to move to the ice. We want to go here, talk about the section number 2 will be ice. Before we talk about the ice, we want to introduce you something. This is called phase diagram of water. Okay, what is a phase diagram of water? You have to draw the picture again. You may be learning in other classes. It's not a new concept. The curve looks like this. Right in the middle is 0 degrees Celsius. This is 20 degrees Celsius. This is minus 20 degrees Celsius. Y-axis, we using mmHg, millimeter mercury column. And you should know a basic knowledge. 76 mmHg equals 1 standard atmosphere pressure. And that is physics. I remember this is 1.03 multiplied by 10 to the 5 Pascal. Okay, here the units up to 15. Okay, so let's do something right here. This is 5. This is 10, and top is 15. Now there's a couple of lines we want to mention. Okay, we always should know water has three phases. What are the three phases? They could directly become a vapor, which is like a gas. They could become ice. It's a solid. Most of the time, it is a liquid. Therefore, we have three lines. What are those three lines? This first line right here.
I think you need to switch the liquid and the ice. Water is ice
Yes,
below
right.
0.
Yes. Correct. This is an ice, this is a liquid. Correct. Okay. What is this curve called? Sublimitation curve. Which means this curve will let the ice the liquid, ice directly become vapor. What is going to be the second curve looks like? Second curve we do here. What this curve looks like? What's that curve? That curve we call vapor pressure curve. What is the straight curve looks like? This is easy. Melting curve. And we want to point out something here. First thing we want to mention is this 0 degrees Celsius. Because we're going to talk about the ice real quick, but the 0 degrees Celsius, we need to emphasize three important information. Sounds like a joke, everybody knows, but we have to emphasize. It's very important. 0 degrees Celsius is melting temperature for water to ice. Now, if it's a pure water, okay, not a purified water, it's a different story. Second, 0 degrees Celsius is a freezing temperature for, this should be ice to water. Okay, melting temperature for ice to water. This is also a freezing temperature for water to ice. You can understand it is solidifying temperature. But more important, don't forget number 3. 0 degrees Celsius is a temperature for ice and water coexisting. They both present there, okay? Co-present, we will also say. So ice and mixed water, their temperature is 0 degrees Celsius. That's the first thing I want to mention. Second thing, when you look at it here, something is dramatic. 5 millimeter mercury column, if you go down a little bit, what's happened? The ice directly become a vapor. Goes here. Okay, so the second thing, at 0 degrees Celsius, if the pressure less than 4.8 millimeter mercury column, the ice will directly become vapor. This is the most important and very simple principle behind freeze drying. We had a facility for that. That's the principle behind it. Okay? So, that's something we want to talk before we talk about ice. Okay. Now, second question, what is ice? From chemistry standpoint, ice is one water molecule mixed with 4 other water molecules. It is still tetrahedral arrangement, but forms hexagonal crystal lattice with halos. That's what's the definition of the ice, using a structure, chemical terminology to explain it. Now, what it looks like? If we cut down ice perpendicularly or horizontally, it will look like a hexagonal structure. Looks like that. And in the center is the oxygen right there. And it's coupled with what? Hydrogen connected. One outside, one in. One outside, one inside. One goes outside, another one goes inside. And this should be not like that. This should be the angle go here. Okay, they go one outside, goes here, one inside, one outside, and one inside. Then goes one outside, and also go one inside. Okay, now there is a little bit of mass behind that. A little bit of mass is that there is a true position for the proton, hydrogen ions. They could connect it with this, or they could connect it with that. So if there is n molecule of water, theoretically, how many positions of the protons will be existing? It is 4n. However, there is a restriction. What is the restriction? Is 2 hydrogen must be connected to 1 oxygen. So, how many different positions for the hydrogen? It is 3 divided by 2 times the power of n. Okay, that's all your textbook. It's just a mass already been existing, talk about these. So these are a little bit about the structure of the ice. We're going to go back to talk about that. Now, what we're going to mention here, the key points, is nucleation versus crystallization. This will be something we want to discuss about that. So give you a very simple example. You can understand it very well. If you have a beef product, you bought from a Kruger, so you're not going to eat today, so you frozen it. Just putting a general refrigerator is minus 10 degrees Celsius. You vacuum packaged or aerobic storage that you put into the frozen to a freezer. Then you took it out 3 months later. It's not going to look very good. You will see the tissue is been cracking. And it's very soft, but it's not tenderized. Because the active myosin cross bridge sometimes will be completely broken by the crystal. So this tells you, in the food processing, we don't like crystallization. Because crystallization will generate a crystal. The crystal could be damaged tissue. So we don't like that. So this comes out with some important concept. So first of all, we have a water there. Okay, water at room temperature, they'll vibrate. So they're actually like dancing. Okay, a very silly dance in the room temperature. Okay, let's say the temperature is decreased to close to 0 degrees Celsius. What's the water molecule they're gonna do? Think about in the cold weather. Last week, what you do? You become very sluggish. So they become sluggish. Like the human being, in the cold weather, they become sluggish. When they become sluggish, what's gonna happen? They will generate an embryo. And this embryo could become a nucleus. And the size of the nucleus, it decided the size of crystal. And also the number of the nucleus decided by the size of the crystal. Large number of nuclei will have a small size crystal, and a small number of nuclei will result large size of crystal. And we don't like this guy because it's going to damage the tissue. So we don't like this guy. So there is a curve comes out, a very interesting curve. Temperature and the nuclear. So this is the temperature and the crystal size curve. So y-axis is temperature. Start from minus 30 degrees Celsius. And we have a minus 20, it's minus 15. Now very good, you draw. So 0. This is a crystal size. Millimeter. What's a curve looks like? Like that. And I tell you one thing. At 0 degrees Celsius, The crystal size almost 120 millimeter. At 10 degrees Celsius, sorry, this is minus. Okay. At minus 10 degrees Celsius, that is almost 50 to 60 millimeter. At minus 20 degrees Celsius, this is about roughly 10 to 20 millimeter. If you always do at minus 40 degrees Celsius, what happened? The crystal size close to 0, which tells you the probability of nucleation is 100% will be happen. But we also want to mention, even at minus 40 degrees Celsius, there is still free available super cold water existing. This tells you to quickly lower down the temperature during the freezing is extremely important. This comes out another curve. This curve looks like this. You go down. This is freezing point. And this is we call super chlorine. What happened? If you're super cold, you dramatically decrease the temperature from freezing point. This curve will decrease dramatically. Crystal curve. And in other words, this curve will be increased dramatically. Nucleation curve.